In this video, we are going to use the results obtained in the previous video for the particular case of the Schwarzschild metric, which is given by the values of the functions lambda and mu equal to 1 minus rs divided by r, where rs, which is the Schwarzschild radius, is given by 2 times the Newton constant, the mass, and divided by c squared, although we are going to set c equal to 1 in this particular video. And basically we will focus on the radial equation, but this radial equation is just the mass shell condition in which we have replaced all the angular variables by the values. Remember, theta was pi over 2, so we are in the equatorial plane, and phi dot was L divided by r squared. Okay, after this substitution, the mass shell condition becomes just a radial equation, which has this form: plus L squared divided by r squared minus L squared divided by r cubed times rs equal to epsilon squared minus 1. And this equation we are going to interpret as the equation of conservation of the energy of a particle moving in just one dimension with coordinate r, and an effective potential that will be given by this expression. Okay, this is what we are going to call here the effective potential, and that we are going to rewrite in this way. So I take a common factor L divided by rs squared, and this multiplies rs divided by r minus rs divided by r cubed. Okay, we can use this expression to work in units of rs. So we could suppress all RS's here if we wanted to. Okay, another thing to notice here is that, well, typically you expect a factor of 1/2. Okay, but this is irrelevant for the kind of analysis that we are going to make. So it is really not important, this normalization. And epsilon squared minus 1 will be the total energy in this effective one-dimensional problem. Well, remember that the energy of the particle is given by epsilon, okay, in units of mc squared. The first thing that we can do is to compare this effective potential with the effective potential that appears in the Kepler problem that it is reviewed at the end of the lecture notes of this particular lecture. And you will recognize the first two terms. This is, after all, the Newtonian potential. Okay, and this term is the term that appears associated to the angular momentum of the system. The relativistic term, the relativistic correction, is described by this third term. And this term has very important consequences. Just qualitatively, okay, you have this negative value that increases when r goes to 0, but then you have a positive contribution that increases when r goes to 0, like 1 over r squared, and which is gives you a much bigger contribution. Okay, as long as L, the angular momentum, is different from 0, gives you a much larger contribution than the first term, and this makes this term to be positive for small values of r when L is different from 0, when there is angular momentum. However, no matter how big the angular momentum is, the problem is that in the relativistic case there is this third term with a negative sign, and this third term brings again the potential to a negative, infinite negative value when r goes to 0. Okay, so qualitatively you see that this is the term that changes everything, especially at small values of r. You don't have to worry too much about those values right now, because we know that the metric is not really valid beyond r equal to rs, or at least for the moment we don't know if it is. as we saw, the metric at r equal rs, okay, lambda vanishes, okay, that's bad. Mu goes to infinity, that's worse. Okay, and this means that the metric is singular there. It is not invertible or anything. It is not even well defined, but because some of the components blow up. So this can be due to the fact that there is something, you're getting too close, for instance, to some point like mass. This could be an explanation. Just like the singularity of the Coulomb field, you get too close to the point-like charge, which is at r equal to 0, and then the field grows infinitely, okay? That could be one reason. And then if that's the case at r equal rs, then the metric inside doesn't make much sense anyway. If this singularity is due to a bad choice of coordinates, for instance, there is a singularity in the Euclidean metric at r equal to 0 when you write it in spherical coordinates. It's singular because you have this term r squared, you have dr squared plus r squared, d omega squared. Okay, then when you go to with r close to 0, this vanishes, and then the metric is clearly singular. It's not invertible anymore. But you know that Euclidean metric is just the x squared, and it is the same and regular everywhere. So here the problem is a bad choice of coordinates. At least these coordinates are not good at r equal to 0. In that case, if this was the problem of the Schwarzschild metric here, again, you could come from the asymptotic region, okay, from far away of the object that produces the gravitational field. You get to r equal to rs, then your coordinates are not valid there, then why should you trust what happens beyond r equal rs? Okay, you shouldn't trust it. Okay, so at the moment we will not worry about what happens beyond r equal rs. But this is anyway the qualitative behavior of this effective potential. And now we can draw it for different values of L, okay, in units of Rs, or if you want, we can represent this effective potential as a function of R divided by Rs, which is exactly the same, okay. Then qualitatively what happens, and this is very qualitative because my drawings are usually so bad, okay. When L is equal to 0, okay, you have something like this. This is just given by this term, the Newtonian potential, and you know what it is like. But when L is different from 0, this part starts becoming a bit flatter, okay, and so this could be, I don't know, L equal to whatever, but anyway, I'm going to increase the value of L. And don't trust my drawings too much. So this becomes even flatter. Of course, this always goes to infinity in the end because of this third term. But anyway, at some point, this starts developing a hump, and okay, I think you get something like this. Okay, this means that if you got this at a constant value of the potential, there is going to be a bound motion between a point in which the total energy, this epsilon squared minus 1, cuts this line, because at these values, okay, the energy will be equal to the effective potential. And if you look into this equation, this is this term is equal to this one, and then r dot has to be 0. And these are the equations of the returning points. So there will be a bound motion. There will be a maximum value of r and a minimal value of r, and this will be bound orbits. Okay, so this is more or less the qualitative behavior. You can see that when L is 0, you always fall into the singularity at r equal to 0. Okay, no matter what is your total energy, okay, you will always hit r equal to 0 if you move to the left, so to small values of r. Otherwise, you will be coming from r equals 0 or from something else. When L is different from 0, In the Newtonian case, you never fall into the singularity because this term dominates, is positive, and there is a potential barrier like this. So you always hit some minimum value of r, and then you go back, and this means that there is a motion that will be something like this. Okay, we know that this corresponds to hyperbolas. Okay, here this is not the case. Okay, and it is possible to fall into singularity, or to go to smaller values of r, even if L is different from 0, depending on the energy that you have. So this is something different, completely different from the Newtonian case, in which whenever you have angular momentum and you don't think on the finite size of the planet or the star that produces the gravitational field, if you ignore that, then you never fall into r equal to 0. Here, this is not the case. Now we can perform a more quantitative study of this effective potential, and as usual, you can study the asymptotic behavior. It's clear the potential goes to 0 at infinity. Okay, this we have seen, but you probably want to compute the extrema of the potential, if there is really a minimum here and a maximum here, as I have drawn, and for which values. Okay, this is the kind of computation that I'm not going to do in full detail, but you want to take the derivative of v with respect to r. Clearly, this potential is really polynomial in rs over r. So the best thing that you can do is to take, well, I apply the chain rule and I take the derivative with respect to r as, okay, the potential. And if I am going to find the extrema, I am going to set this equal to 0, and it is enough to solve this part, because this is just different from 0. And what one finds, if v is a cubic polynomial, then v is a square polynomial, and you can find the roots using the standard formula, and what you get is that the two extrema are given by a place at this point. 1 minus 3 rs divided by L square. Okay. Now we have to find out if they are minimal or maximum, but something that you have to you can immediately read from here is that certainly 3rs divided by L squared has to be smaller than 1, otherwise smaller or equal than 1, because otherwise this becomes complex and there are no extrema whatsoever. This gives you rs divided by L. This is smaller than 1 over the square root of 3, and then L has to be always larger than the square root of 3 times rs. Okay, otherwise, for smaller values of the angular momentum, there are no extrema whatsoever, and you don't expect bound motion in Okay, then the next thing is to find out if these two extrema are maximal or minimal. For this you have to compute v double prime and evaluate it at the value of you want r extrema divided by rs, which you can get from here just like this, and okay, finding whether this is positive or negative, what you find is that with the upper sign, which is a minus here, so this is going to be maximum, so I can write S 1 minus square root of 1 minus 3 S divided by L. Okay, and the minimum value is 1 minus 3RS divided by L. Okay, clearly R min is larger than R max, and this corresponds to this drawing. R min will be more or less over here, okay, and R max has occurs at a smaller value of R. Knowing these two values, okay, and this critical value of the angular momentum, then we can study different kinds of orbits of different situations. So when L is smaller than L critical, which is a square root of Rs, so there is no maximum or minimum, there are no bound orbits, and just particles fall to R equal to 0. And one important case, okay, so this is the first thing that we are going to study, but one important case, which is the simplest, would be particles falling with L equal to 0. So they are directed to R equal to 0 with some value phi equal constant, okay? And yeah, because remember that phi dot was L divided by R squared, so now phi dot is 0, so now phi is equal to phi 0. Theta was given by pi over 2, and this particle will go, if it starts somewhere far away from the center, it will fall naturally to R equal to 0. So let's suppose that at tau equals 0, the particle starts with vanishing radial speed, and from a starting point, which we call R0. So it sits at some distance, we are there, and we release it. We just let it fall, okay? The questions that control this fall, which is described as in Z's book, in Anthony Z's book, as a radial plunge into R equal to 0, are T dot, remember that it was epsilon divided by lambda, and we only need the mass shell condition, okay, which in this case, because S is 0, just takes this form, epsilon squared minus 1. Okay, we can evaluate this condition at tau equals 0, because it will give us the value of epsilon. So at tau equals 0, okay, maybe the arrow should take the other direction. This will be Rs. R is the initial radius, and this is epsilon squared minus 1. So this is just this, and epsilon is this, which you can view more or less as the potential energy. This would be the potential energy and the mass of the energy due to the mass of the particle. Remember that the total energy is minus this value multiplied by mc squared. Okay, so knowing this, the radial equation becomes r dot squared equal to epsilon squared is 1 minus rs divided by r0, and then you have minus 1 minus rs divided by r. Okay, these factors of 1 vanish, and you have rs 1 over r0 minus 1 over r. with a minus sign, so maybe I invert the order. Okay, which is okay. Now this is clearly positive because R0 is larger than R, and R dot square should be positive. And now we can take the square root of both sides of the equation, and we get R dot equal to Rs 1/2 and the square root of 1 over R minus 1 over R0. And in principle, I have two possible signs. Which sign should we take? If we want to describe the motion of falling into R equals 0, or it is a motion in which R decreases from R0 towards R0, from R0 towards R equal to 0. This means that the derivative of R with respect to tau, since tau always moves forward, will be negative, and this means that I have to take the minus sign, okay, and this is associated to falling towards R equal to 0. Now we can integrate this. This will be the R over the tau. This is just a function of R that I can take here, and we get the R divided with the minus divided by 1 over R minus 1 over R0 equal to the integral of Rs 1/2 d tau. Okay, well, I took the integral in one side, and of course now I take it in the other side. This integral is can be performed by substitution and the usual techniques. You can find it. You can find exactly how it has been done in the lecture notes. Then what you find is that Rs 1/2 tau, which is the integral of this side, is equal to minus R0 3 over 2 arc sine R divided by R0 to 1/2 minus R divided by R0 1/2 square root of 1 minus R divided by R0 plus an integration constant which is fixed by imposing that at tau equal to 0 R is equal to R0. Okay, this means that so tau equals 0, the left hand side is 0 equal to minus R3 2, and then the arc sine of R divided by R0 1/2 is arc sine of 1 minus, and this is 1 but this is 0, so you just get this, and the arc sine of 1 is pi over 2. Okay, this plus c, which means that c is R0 3/2, and this multiplying pi over 2. Okay, so this is the final result. Okay, for what it's worth, you have this arc sine R divided by R0 to power 1/2 minus R divided by R0, the square root of 1 R by R0, and minus pi over 2. Okay, or if you want to change the sign here everywhere, okay, you can write it in this way. You probably would like to have R then R as a function of tau, but this is clearly impossible. Here R is just implicitly a function of tau. So actually have tau as a function of R. So what can you do? Or what can you learn from this equation? For instance, you could try to see something interesting is what is the value of tau if you start from R larger than, so R0 larger than Rs, and you approach this singular point R equal to Rs, what is the value of tau? Okay, So, okay, what you want to compute is you want the limit when r tends to rs of 1 over rs 1 half, r0 3 halves, and everything that you have here. And the value doesn't matter very much. The only thing that should be important here, okay, is that because R0 is larger than Rs, okay, when you approach this is smaller than 1, so this is okay. Here this R0 is also larger than Rs, so R divided by Rs will always be smaller than 1, so this is again okay. So this is finite and also real, okay, you don't get anything special, but most of it is a finite real number. Okay, this is what happens to the proper time. This means that if you are somebody falling spontaneously, you are released at some distance from this singular point Rs, and you just are let fall into this gravitational field, you will reach Rs in a finite proper time. Okay, you can estimate more or less what it is just using numbers, but the important physical question is that, or physical point is that it is finite. Okay. However, because this differential, this is equal to epsilon divided by 1 minus Rs divided by R. Okay, remember that this is tau dot, and this is epsilon divided by lambda. Okay, this derivative diverges when R approaches Rs, which means that the time that will be measured by an external observer, okay, in these Schwarzschild coordinates, and this observer is measuring how long it takes for you to reach R equal to Rs, this time goes to infinity, so it never sees you cross this region or reach it, in fact. Okay, and this discrepancy, which is what it is, you cannot fix it. Okay, and we will not fix it when we study black holes in lecture 7 or lecture 8. This is in fact a characteristic of black holes. Is one of the main interesting things, and well, you have to accept that it is like this. Okay, we will see more about it, but there is really a discrepancy between the observations of somebody falling into the black hole, who will cross this region R equal Rs in a finite time, and the observations of an external observer at rest with respect to the black hole, who will never see you cross this R equal Rs region or even approach it. Okay, we will see that later. Then the other kind of orbits which we can study are orbits in which the angular momentum is larger than this critical value. So there is a minimum and there is a maximum of the potential. Okay, and then in principle bound orbits are possible. The potential is something like this. Okay, and then it goes again to minus infinity because the relativistic term dominates small values of R. Okay, there are three different cases, or three different possible motions in this situation. These three different motions are characterized by or distinguished by the value of this effective energy that appears in the equation of motion up here, well, really up here. Okay, in this effective problem, so this is the effective total energy with respect to the maximum value of the potential, which is here, and the minimum value of the potential. There are three possibilities. First of all, the total energy epsilon square minus 1 can be higher, and this is the first case, than the value of the effective potential at R max, which is this one. And you see that in this case you fall to R equal to 0 if you move into this direction. So if R is equal to 0, so if this is the origin R equals 0, then okay, this is not a radial motion because L is different from 0. In fact, it's larger than the critical value. But what happens is that no matter what, you will fall into R equal to 0. Okay, so this is the first things that can happen, and you see a difference with the Newtonian case in which you always find a barrier, a potential barrier in this effective potential when you have L different from 0, and then no matter how high this total energy is, you will never reach R equal to 0. The second possibility is that your total energy is over here, so it is smaller than R max. Okay, so we can put it like this: E effective R max is larger than epsilon square minus 1, which still is positive. Okay, so it goes like this. This means that it will never touch the potential over here, so it is not a confined potential. It only finds a potential barrier in this side, and the particle will be scattered. Okay, so something like this can happen. Okay, if the particle comes from infinity, it will reach a minimal distance. Well, the way I have described it, this is not the minimal point, the minimal distance. The minimal distance will be this one. So let me draw it again. So this is R equal to 0, and the particle comes and does something like this. Okay, and this is supposed to be the minimal distance, and this minimal distance, this is just R max. Okay, so it comes from infinity and goes back to infinity. And the third possibility, okay, this is the one that leads to bound orbits, is the one in which this total energy is smaller than 0, but the only way in which this can be consistent is if this is still larger than the minimal value of the effective potential. So this is a motion over here. Okay, and if it is smaller than 0, no matter how small this value below 0 is, it will touch the potential at some point because this potential goes asymptotically to 0. This means that it will find two potential barriers, one over here, another one at some other point, and you have a bound motion. Okay, and this motion will be, if you want, elliptic-like. After all, this the third term that we find, the relativistic one, at some distance. Okay, and here the distance will always be larger than R max. Okay, so motion here is just a correction because it goes like 1 over R cubed. It's just a correction with respect to the Newtonian potential. Okay, now we should find what are the characteristics of these orbits. Okay, so the orbits are contained between the 2 points at which R dot is equal to 0, and this is what happens. This happens when the effective potential is equal to epsilon squared minus 1. These are the 2 points at which this line of constant energy cuts the effective potential. And well, this equation, since this is a cubic polynomial, there are in principle 3 roots, and it seems that you only expect 2, but of course there is a third root which corresponds to this point that doesn't really matter to us. Okay, So we are really interested in these two, which we will call R plus and R minus. And this third root we will call R0, which has nothing to do with the R0 of the radial planchet that we studied before. Okay, and since this is a cubic polynomial, finding the roots is not so simple, and the way to do it is to identify, so you rewrite this in this way, as epsilon squared minus 1 minus Vf of R equal to 0, and now this cubic polynomial, whose roots you want to find, well, you know that it can be written in this way. 1 over R minus 1 over R plus, and 1 over R minus 1 over R minus. Okay, and this is what you want to find, this overall factor k that we have normalized in some standard way. And you also want to find the values of R0, R plus, and R minus. And the only thing that you have to do is to identify these two things and start solving the equation. Now, if you try to do what I just said, and you try to find R0, R plus, and minus as functions of the parameters that appear in this cubic polynomial, is a cubic polynomial in 1 over R, of course. So you could try to find these three numbers, or these three constants in terms of epsilon, L, and Rs, which are the three parameters that appear in the effective potential and also here. Then you, not so surprisingly, will find that you have to solve again cubic equations, which is not so nice. Then it is useful. It turns out that people have thought about these problems for a long time, and it turns out that it is very useful to make a change of variables and replace R plus and R minus by the orbital elements. Okay, this is inverted. Okay, if you look into the classical Kepler problem, the solution is given by E cosine phi minus the initial value of phi. So the two extremal values of R are reached when cosine, this is cosine of 0 or pi, and in that case you get plus or minus E. When it is minus E, this is the maximal value of R, so this is R plus, and when it is the other value, this is the minimal value. Okay, so this is the origin. As you know, this P is known as the semilatus rectum, and E is the eccentricity of the elliptic orbit. Okay, this doesn't mean that the orbits that we are going to find are elliptic. We're just using this, if you want, elliptic inspired constants or variables. Okay. But this doesn't mean that the orbits are going to be elliptic, because we know that they are not going to be elliptic. Introduce another parameter, which we call capital E, and it is not the same E that we saw before, and which is defined by epsilon squared minus 1, and which will be related to the Newtonian energy in the appropriate limit. Now we can substitute this R plus and minus here and here, and start relating the coefficients of the expansion of these two polynomials, the independent term, the term which is proportional to R, to 1 over R squared, and so on. And then we are going to find the following relations, which are found in the lecture notes. These computations are straightforward, so I will not repeat them, and I will just put them here. Okay, the value of R0 is this one, L squared, and so on. You could try to solve for P and E in terms of L squared, E, and so on, but this is, well, this is not very useful. What is more useful in this form is this form, And for instance, because we can study the Newtonian limit. You should recover the Newtonian limit when the orbits are very large, because then gravity is weak, the velocities are very small. Okay, since the average radius of the orbit is more or less given by this p, because r plus is larger than p. Okay, it is p divided by 1 minus e, which is smaller than 1, so it's larger than p, and r minus is smaller than p. You can take p as a proxy of the average radius, and then you can study this the behavior of these expressions in the limit in which rs divided by p goes to 0, which is more or less the Newtonian limit. The limit of R0 doesn't concern us very much, because R0 is just not there in the Newtonian case. But the limit of L squared, which is easy to see, is RSP divided by 2. And then you can check that this is exactly what happens, or what we found in the Euclidean case, and the same for E. This is just, well, it goes like, okay, because if we go to 0, minus rs, sorry, the way this is written is like this, 1 minus e squared. Okay, so now, okay, what are I? By assumption, we have that R0 should be smaller than R minus, and which should be smaller than R plus. Okay, R0 is given here. It is Rs divided by 1 minus 2 Rs divided by P, and R minus is P divided by 1 plus E. Okay, this is automatically smaller than 1 P divided by 1 minus E, as long as E is positive, which we always assume. So if you just solve this inequality, you find that P, which is this average radius, is always larger than the Schwarzschild radius times 3 plus the eccentricity. Now we can go a bit further. The motion that we are describing, this bound orbits, is a motion which is periodic in the variable r. This doesn't mean that these orbits are that we have closed orbits or anything like that. It just means that certainly you are going to start, for instance, in r minus. The particle will move to r plus, and then will come back to r minus, and so on, cyclically. Okay, so it is useful to introduce a new variable, which we will call chi, and which in general we have to stress that it is different from phi, although for the Keplerian case it will be identical to phi. So chi is an angular variable that takes values between 0 and 2 pi, and which is defined by this property. Okay, it is the fact that r as a function of chi will take this form, which is exactly the form that the Keplerian orbits have as a function of phi, but now it's in terms of chi. Does this mean that the orbits are ellipses? Well, they are not in general, because chi is not phi. So if you represent this in the r phi plane and r phi coordinates, this will not be ellipses. In the r chi plane, yes, but chi is not phi. Okay, so I hope this is clear. Okay, so what you have is that when chi is 0, so you have r of 0, this is p divided by 1 plus e, which is r minus. Then when chi is pi, you have r of pi, and this is 1 minus e, which is r plus. And again, when you reach the value chi equal to 2 pi, you come back to r minus. Okay, so now the idea is to rewrite all our equations in terms of chi, phi, and t instead of r, which has been replaced by chi, because the relation between chi and r has been fixed. You can understand this as a change of variable if you want. So how you change variables, okay, and all the equations and all the relations that we have. So wherever we have r dot, which is the derivative of r with respect to tau, we take the derivative of r with respect to chi, and then we have the derivative of chi with respect to tau. Okay, this derivative, well, we just have to compute it from this formula, and it gives you 1 plus e cosine chi squared and p sine chi, and then you have chi dot, which is not known. Okay, some other terms that you need to translate into the new variables are 1 over r minus 1 over r plus and 1 over r minus. Okay, so this is 1 plus e cosine chi divided by p minus 1 minus or plus e divided by p. And if you collect all the terms, this is p, and these terms cancel, and you have e cos chi plus and minus 1. So if now you compute this, which is one of the things that appears in this effective potential, this becomes just, okay, minus, this is the product of these two things, so it's minus e squared sine squared of chi after you convert cosine chi squared minus 1, okay, divided by p squared. You can also translate into these new variables 1 over r divided by r0. Okay, this is given by the definition of chi, and this one, we computed it before, so it's 1 minus 2 rs divided by p divided by p rs divided by p. Okay, and then you just compute things. This is 1 over p, 1 plus e cos chi minus 1 over r s divided by p plus 2. Okay, I'm not going to repeat all the calculations. The only thing that we really need in the end is what appears in the other side. So you have, remember that we had r dot squared plus v of r minus 2e equals 0, or if you want this equal to 2e minus v of r. Okay, so this piece here is the one that we that was a cubic polynomial and was factorized and so on. So it has this factor times this, and times k, which we already was computed in the lecture notes. And in the end, what you get here is a function of sines and cosines of chi, very complicated, that you can find in the lecture notes. Okay, but this is just a function of chi. Okay, here you also get, well, this is what we have computed here. Okay, so functions of chi times chi dot, and in the end you can extract from here an equation in which you have chi dot and a complicated function of chi that I'm not going to even try to write because it's just long and not very illuminating. Okay, so this is what happens with the equation with the mass shell condition. which we have used as equation for R. Now we have to do the same with the other two equations. So we have, for instance, the equation that involves phi dot. So just to do it exactly in the same way in which it is done, sorry, in the lecture notes, you see that this is d phi, d tau, d chi, or phi dot over chi dot, and remember that phi dot is L divided by R squared, and you have 1 over chi dot, for which we found already an equation. We also have an expression of R squared in terms of chi, which is just this definition of the variable chi. So we plug this in here, and you get, in the end, an equation which is not so complicated, and which I will write explicitly in this case. It's just 1 over the square root of 1 minus 3 plus E cos chi Rs divided by P. Okay, and well, a nice check of this equation is that if Rs divided by P goes to 0, which remember was a way to recover the Newtonian limit, this term goes to 0 and d chi over d phi goes to 1. So phi or chi is equal to phi in this limit, which is what we expected, because you have to recover the Newtonian orbits or the Keplerian orbits in which this chi becomes phi. Okay, the last equation that you have to translate into the new variables is the equation of t, and okay, it's not so complicated. You just write t dot over phi dot, and I mean chi, and you write it, and so on. I'm not going to write it explicitly. Okay, so even though we are not going to integrate explicitly these equations, there are things that you can find from them. In a complete cycle, and a cycle is, remember, going from R minus to R minus again, or from R plus to R plus, but we have chosen the convention that you start from R minus. This is chi goes from chi to chi plus 2 pi, and when this happens, phi will go from phi to phi plus some delta phi, which we don't know what it is. Okay, this delta phi will be 2 pi only in the Keplerian case. T goes to t plus p, which is the orbital period. It is the time in which it completes one orbit, but the one orbit means here going from the pericenter back to the pericenter. Okay, so this is the orbital period, and okay, tau will go from tau to tau plus this calligraphic p, which is the proper period, which is the period measured in the proper time. So if you are an astronaut in orbit, okay, this will be the period that your clocks will measure. Now we can compute this delta phi by integrating in a complete circle d phi over d chi. Okay, and the same you can do with the orbital period, sorry. So you integrate dt over d chi, which is given by those expressions with respect to chi, and the proper period. Is again an integral from 0 to 2 pi of d tau d chi d chi. This is just 1 over chi dot, but you have to compute chi dot. Since we have expressed this as a function of chi, this could be integrated and the same for this, okay? So you could in principle compute delta phi and p exactly, okay? So you can do it numerically, and you can do it also approximately. For instance, in an expansion in the parameter rs divided by p, because this is, if you want here, our post-Newtonian parameter, the parameter that which when it tends to 0 gives you back the Newtonian result. Okay, this is done in the lecture notes. It has no mystery, it's just some calculation. Okay, and the result for delta phi in this approximation is 2 pi. This is what you expect. This could be the Newtonian result and comes from the first term. So clearly d phi over d chi will be, chi will be phi plus corrections, or you can express as phi equal to chi plus corrections, which are post-Newtonian corrections, because the Newtonian term would be chi equal to phi or phi equal to chi. And this gives you 1 in this integral, and from this one comes a factor of 2 pi, and then you have another term which is 3 pi rs divided by p, and another term that you can compute which is 3 pi divided by 8, 9 plus e squared rs divided by p squared, plus terms of third order in rs over p. Now you can search in internet what are the values that you should consider for rs, p, and e if you want to study what is delta phi. For instance, for Mercury. In that case, so if you want to do it for Mercury, and okay, notice that this is an approximation in which we are dealing with Mercury as a test particle moving in the field of the Sun, whose rotation, oblateness, and so on we are ignoring. So this is, if you want, the leading term of a more precise calculation. Okay, so if it is for Mercury, Rs is the Schwarzschild radius of the Sun, okay, which is the one that produces the gravitational field, and this is more or less 3 kilometers. You can find in the Wikipedia or anywhere else the eccentricity of the orbit. This is 0.21. Okay, it's at 0 point. And the semi-major axis of the ellipses, which is A. And this A is defined as 1/2 of r plus r minus, which is, according to our definitions, just p divided by 1 minus e squared. And this, you find that the value is 5.8 times 10 to the 7 kilometers. Okay, from this you find p, because p will be 1 minus e squared times a, and this is 5.5 times 10 to the 7 kilometers. And finally you have rs of the Sun divided by p, which is 5.5 times 10 to the minus 8. Okay, you introduce this in this computation, and what you want really is the anomaly. Okay, the normal value would be 2 pi of delta phi, so you want delta phi minus 2 pi, and this is essentially 3 pi times 5.5 times 10 to the minus 8, which is 5.2 10 times 10 to the minus 7. And this is obviously per cycle, okay, or revolution. Okay, so this is not a closed orbit. Probably here is the sun, and you have this would be R minus, this would be R plus. Okay, they are supposed to be centered here. Okay, it's just my drawing. And so Mercury does something like this. Okay, it comes back, it touches here, but the next time it is displaced a bit to the other side and so on. Okay, so it's never a closed orbit, but there is a good notion of what a revolution is, or a period. Okay, here this is very, very exaggerated. So revolution consists in touching R plus 2 times, or okay, so between here and here, this is a complete revolution, or 2 times R minus. Okay, now you have to multiply by the number of revolutions per century, okay, in order to find what is this very small number. And this is using the period, okay, which is 7.6 times 10 to the 6 seconds. You find that since a century is more or less 3.210 times 10 to the 9 seconds. This means that Mercury takes 421 revolutions per century. And so you want to multiply this number, delta phi minus 2 pi, times 421, to find out how many, what is the shift of this perihelion in angle. Okay, so okay, but probably you want to do it with the other side. So accumulated in 1 century, so you multiply this and you find that this is 0.00022, and this is given in radians. Okay, we are working in those units. If you translate this to sexagesimal units, you find that this is 45.3 seconds per century. The right number is 42.9, but we have per century. But we have rounded out many numbers, so this discrepancy is normal. Another thing that you have to take into account is that there are many other effects that one has to take in this calculation if you want to do this more accurately, like the bloodness of the sun, effects of the rotation, and so on. And if you observe this shift of the pericenter, you have to you would realize that is several thousands of seconds per century, and that's because there are many other effects which are much more important than the general relativistic effect, and those are the influence of other planets and so on. They are much larger. So really this anomalous shift is really the part that could not be explained away by the influence of other planets and standard Newtonian effects. The Newtonian theory is so good that it could explain away several thousands of seconds per century, but this 42.9 remained unexplained. The simplest explanation would be that there was another planet who nobody had yet observed. Okay, this is not so ridiculous because that's the way some planets were actually discovered due to the gravitational effect on other planets. So people searched for this planet and they didn't find it. Okay, and well, in the end, it turned out that Einstein did this calculation, and he just found the number that completed. Well, this was the missing shift. Okay, the rest was already explained. Some people may establish a parallelism between this story that I just told you and dark matter. People explain, dark matter is known only through its gravitational effect on the visible matter. So the simplest explanation is that, okay, this gravitational influence, these anomalies in the motion of the visible matter, planets, stars, and so on, is due to some matter that we don't see, like this planet that nobody was seeing. So some people think that a better explanation would be a modification of gravity, especially because just like nobody has ever seen and nobody ever saw this new planet, nobody has yet detected a particle of dark matter. So the alternative explanation is still there. But to tell you the truth, dark matter is a problem that happens at several scales, not just at the scale of motion of some stars or galaxies or so on. It is also it has a cosmological scale side, and it is not so easy to cook up a modification of general relativity, especially one that explains this effect at the scales of galaxies and also at the cosmological scale. So for a moment there are attempts really to explain what we call dark matter, or the effects, the gravitational effects produced by what we call dark matter have failed, in the sense that we don't have candidates for dark matter. Nobody has detected that. And on the other side, alternative modifications of general relativity do not seem to work well enough to explain this effect that we call dark matter, and at the same time keep explaining everything else that general relativity explains. Now, to end this discussion on bound orbits, we're going to consider the case of circular orbits. Well, they correspond to the case in which the energy of the particle, if the effective potential has this form, which I am exaggerating, of course, when the energy of the particle corresponds to the maximum of or the minimum. But this one corresponds clearly to unstable orbits, and the stable circular orbits are these ones. Now, these orbits exist whenever there is a maximum and a minimum. And remember that R max, and R max and R min is not the same as R plus and R minus. R max and min remember they were given by these two expressions, minus and plus 1 minus 3rs divided by L squared. Okay, so they exist whenever these two maxima and minima are well defined. Okay, although one of them, the circular orbits which correspond to R plus are unstable, but the other one is stable. It's stable unless these two values coincide. This is a limiting value that tells you what is, beyond that, there will not be any stable circular orbit. And this happens when R max is equal to R minus, and this is when 1 is equal to 3 Rs divided by L squared, and this is when you get you reach this limiting value of LC, which is a square root of 3 times RS. When this happens, okay, this is you have this minimum angular momentum. The maximum and the minimum coincide, and this is the limit for which there is a stable circular orbit. The radius of the circular orbit for which this is true is called the radius of the innermost stable circular orbit, R_, and you can check that it is 3 times the Schwarzschild radius. Well, how do you compute that? Okay, because you have that this happens when these two values are the same. This would be R_, and this is when this vanishes, so you get L squared divided by RS, and this vanishes when L is LC, and LC is a square root of 3RS, so you have R3RS squared divided by RS. So this is how I have computed this radius. Then if you have objects whose radius, or the radius of a star, or something else, typically will be a black hole or a neutron star or something like this, is smaller than this limiting value, you will have this object, and okay, this will be R_, and you will have matter rotating and accreting around this object. Okay, this matter will radiate because of collisions between the particles that contain that compose this matter. They will lose by energy and angular momentum until they reach this value of the radius. The moment they lose any more angular momentum, they just fall to whatever you have inside. That will be a black hole, a neutron star, or something like that. If you want to estimate how much energy is radiated by a particle which starts at infinity, okay, at some time, and it's at rest there and falls to this value, okay, of the radius, you will see that okay, you can check that the energy, this computation is done in the lecture notes, that the energy that it has at infinity minus the energy that it has at this orbit, okay, normalized to the energy that it had at infinity, is 6%. So 6% of the total energy is radiated away. If you want to compare what is with the percentage of energy which is released in nuclear fusion, well, that is just 0.7%. This explains why these processes, okay, accretion around black holes or neutron stars or things like that, release so much more energy than any other process in the universe. Though gravity is the weakest force, well, the potential well of gravity really goes to minus infinity. So you start from zero, you can extract really a lot of energy. All the energy that a particle falling in this potential will release will be radiated away, and it will be a lot more than in nuclear fusion. Now let us consider the massless case. In general static spherically symmetric metric, we manage to rewrite the mass shell condition in this form, plus what we call V0 of R, and this V0 was given by a half of 1 over R squared minus 1 over B squared lambda mu. Lambda and mu were the two functions that appear in the metric, and b was just L divided by epsilon, and I had the interpretation of the impact parameter. Now for the Schwarzschild metric, in which mu is equal to lambda equal to 1 minus rs divided by r, if we multiply by 2 this equation, just to write it as we did in the massive case, we find that this takes the form r dot square plus 1 over r square minus rs divided by r cube equal to 1 over b square. The other equations that we had to solve take exactly the same form. This was epsilon divided by lambda, so it is 1 epsilon divided by 1 over rs divided by r, and phi dot is still L divided by r squared. These are the three equations. We can just proceed as in the massive case. Now we call this effective potential capital U of R, and we study this potential. Okay. It's 1 over r squared minus rs divided by r cube. And you see that now this is different from the massive case. There is no 1 over r term. The first term is 1 over r squared, and it is positive. Okay, and you have this correction. Well, both terms are clearly relativistic in this case, but there is another term which is cubic in 1 over r that dominates for small r. This one will dominate for large values of r. Okay, so you can find what are the minima of this potential, taking derivatives, and you see that there is only a maximum. Okay, so this happens for R max. I am advancing the fact that it is a maximum, and R max happens to be equal to 3 rs divided by 2, which is larger than rs. Okay, so we have no problem in considering this point, okay, because it is further away than the Schwarzschild radius, where we have the singularity that we still don't know how to deal with. Okay, and you can find the value of UR at R max, and this is 4 divided by 27 rs squared, which is positive. And okay, with this data, knowing all this, you can draw qualitatively at least this u of r as a function of r. Okay, as we said, for large values of r, this is 1 over r squared dominates, and it is positive, so it's something like this. Then there is a maximum, and then the other term, the term in 1 over r cube, dominates, and the maximum will be at this r max equal to 3 halves of the Schwarzschild radius. This is basically the shape of this potential. Then there are different cases. Okay, here in this effective one-dimensional problem, 1 over b squared plays the role of the energy of the particle in this effective problem. Okay, so the first case that we can consider is the case in which 1 over b squared, this energy, is smaller than u max. Okay, this we call u max, and corresponds to this value, u max. So if it is smaller, okay, the energy is like this. It will find this potential barrier, and okay, this particle will be deflected. Okay, it comes from infinity, reaches a point of maximal approach and then goes back to infinity. This condition, so particle is deflected, and you can check that this means 1 over b squared is smaller than u max, means for b that b is larger than 3 square root of 3 over 2 rs, which is more or less 2.6 rs. So you have your sun or whatever, or your star. This is the center, okay? Well, deflection will take place whenever your light ray is emitted with a p which is larger than, well, this is supposed to, let me start again. This is the center, this is your star, and suppose that this is this 3 square root of 3 over 2 rs. For a star, really the normal star will always be larger than this radius. This is only good for maybe neutron stars, I'm not so sure, and for black holes. So, but in these conditions, if b is larger than this, okay, of this b, light will be deflected. So, well, something like this will happen. I am exaggerating again, but something like this. Okay. So another case is the case in which b is exactly 3 square root of 3 over 2 rs. Okay, you can check that in this case there is an unstable circular orbit. Okay, this is more or less apparent because in this case you have exactly this energy, and the radius is 3 over 2 rs. Well, if b is smaller than 3 square root of 3 divided by 2 rs, well, light just falls into 2r equals 0. Okay, all these behaviors are really relativistic in the Newtonian theory, unless you adopt the point of view that light is made of massive particles. Light as a wave would not be deflected by a gravitational field. Now it is, and you have all these effects. The more extreme one is light being completely absorbed. Okay. We are going to study in more detail the deflection of light, which is the effect which is observable, because if light falls in, you cannot see it, in the next video.